so 3.1 is really an extension of 2.4. It's truly the exact same thing, but we're formalizing the concept of derivatives. So the two big new concepts in calculus are derivatives and integrals, and this is starting the derivative section. So first of all, I want you to notice this, we mark derivatives as f prime of x, and notice this. The limit as h approaches 0 of f of x plus h minus f of x over h is exactly like what we did in the last chapter. Okay, so we're just, now some of you are not good about writing the limit as h approaches 0. You're not going to get credit if you don't write that part down. Okay, so let's look at what this is. So differentiate, which means find the derivative, which is f prime of x equals the limit as h approaches 0 of f of x plus h minus f of x all over h. Okay, so that's going to be the limit as h approaches 0 of x plus h cubed, because I'm just plugging in x plus h in for my x's here, minus f of x, which is x to the third, over h. Now, if you need to go over here, f of x is x to the third, f of x plus h is x plus h to the third. That's fine. But you need to write the limit as h approaches 0. Otherwise, you can't plug 0 in for h. This is the whole point of writing that. Okay, if I need to expand x plus h to the third, so truly the easiest way to do this is using Pascal's triangle. If you remember this, these are the coefficients when I expand this. So think of it when it's squared, it's 1x squared plus 2xh plus h squared. So when we're raising it to the third, it's x to the third plus 3x squared h plus 3x h squared plus h to the third. We're just using Pascal's triangle to save us a lot of time and effort. If you need to take the time to do 3 of these and multiply it all out, you can absolutely do that. I would say this is the smartest way to do it. All right, now we're going to cancel everything that doesn't have an h. And then we do the limit as h approaches 0. We can actually factor the h out. Remember, this is the point where this should have been squared. Sorry. You want to factor out everything that doesn't have an h. Then you can cancel the h. And then you can plug 0 in for each h. And we're left with 3x squared. What this is telling me, the derivative of x is 3x squared if f of x equals x to the third. Okay, sometimes that, I would say we use that definition 90% of the time. There are occasions, and I'm going to say with square roots, we're going to use this alternative definition. So go ahead and write this equation down. Notice f of a is all of those places. All right. Okay. So we have to find f prime of a, take the limit as x approaches a of f of x. I'm just going to write this down. And then I'm going to use this here. So I'm going to carry down the limit as x approaches a of the square root of x minus the square root of a over x minus a. All right, now at this point, this is where it gets a little math sneaky, and you got to remember some of your pre-calc and fixing to fix it. Hang on just a second here. But we're going to multiply top and bottom. In order to fix this, I'm going to multiply top and bottom by the conjugate of the numerator. All right, so when I multiply by the conjugate, first of all, I'm going to bring down the limit as x approaches a. My numerator, square root of x times square root of x is x. The middles end up canceling when you multiply conjugates. Minus radical a times radical a is a. So this is helpful. I'll just put this down here. Because notice I couldn't plug a in way up here because I would get 0 in the denominator. So when I manipulate this algebraically, multiplying top and bottom by the conjugate, I can now cancel a common factor. I can now plug a in here. I have to keep my 1 on top to hold everything in the denominator. And I get the square root of a when I plug it in for x plus the square root of a, which is 1 over 2 square roots of a. That's the derivative of the square root of x. All right, so this is super important. People in the beginning get very confused at all the different ways that we can talk about derivatives. So earlier I said we read this f prime of x. We know that f of x is the same thing as y, so we can also say y prime. We can also, you're going to see this a lot, and this is the one people are the most uncomfortable with, but we read it as the derivative of y with respect to x. This is going to be important because we're going to use this a lot later on. So notice they just also now replace this y with f, or the whole thing with just f of x. So just write down each of the notations that all of those indicate that you need to take the derivative. You don't need to write all the wording down, just recognize the notation over here. Okay, so graphing f prime from f, this is a little tricky. People struggle with the graphs overall. And what I want you to think about, in this case, my y is f of x. If I want to graph f prime, my y turns into f prime. Now, think about what we've talked about in the past. When we're doing this equation, it's the slope of the tangent line. And what this is saying, the slope is the derivative. The derivative is the slope of each tangent line along the curve. Okay, so what I'm going to do, I'm going to create points. My x values remain the same. 1, 2, 3, 4, 5, 6, 7. But my y values will now take on the slope. So this says at 0, at point A, has slope 4. So that means the coordinate point is going to be 0, 4 for the derivative. Because now x is the same x value, but my y value turns into the derivative, which is the slope. So my new point on the derivative graph is 0, 4. It tells me at point B, which is almost to 2, is slope 1. Then at C is slope 0. That's just a little bit past 2. Then -1 is at about 3. And 5 is also -1. And at 6, it's 0. So I'm going to connect my dots to make my derivative slope. This we will practice on for months, so don't freak out too much. Now we're going to go backwards. We're going to start with the, notice, derivative, and we're going to go backwards. All right, so we're going to create a graph. And this is really critical. They give us a starting point of 0, 0. Now, notice this right here. This is telling me my slope is the derivative, is -1. That means from where x is 1, because everything's in the same x value, where x is -1, this is a straight line with a -1 slope. Well, guess what? In order to go through this point, I have to go down 1, over 1, creating a -1 slope. And I'm just going to go backwards. A horizontal line on the derivative corresponds to a straight line on the original. The next part that's important, f is continuous. So I'm going to use this point to start to go to the right. Well, what is my slope as x is greater than 1? Because all y values are 2, this part's telling me the slope is 2 on the right side. So I'm going to go up 2 over 1, creating a continuous graph with slope 2. All right. One-sided derivatives is kind of like one-sided limits. It's just saying there's differentiable from the right or from the left. Notice the right hand is where there's a plus by the 0, and the left is the negative by 0. That's really all this is talking about. All right, so the last problem, typically where we see this is with piecewise functions. And so what we're going to do is we're going to find the limit as h approaches 0 from the left of that. Now, we're only going to check at 0, so let's go ahead and just do 0 plus h minus f of 0 over h. So if we're coming from the left, I'm only going to use x squared. All right, so that's going to be the limit as h approaches 0 from the left of, when I plug in 0 plus h squared, I just get h squared, minus f of 0 is just 0, all over h. So really I just am left with h, and if I plug in 0, my slope is 0 from the left. Now, let's find the limit as h approaches 0 from the right. So we're going to do f of 0 plus h minus f of 0 all over h. Notice each time I write this, I'm writing the limit as h approaches 0. This time I have 2h minus 0 over h. because this time from the right, I'm plugging it into 2x. So this time I get 2. Notice these are not the same. So we say there is no derivative at when x equals 0 because the derivatives are not the same from the left, from the right, just like limits. Now, what's maybe a little helpful, if I graph this, because on the left it's just the left side of the parabola, do you see how this is approaching a 0 slope here? Then I have a line with a slope of 2 on this side. So on this side m is 2, on this side the slope is approaching 0 from the left. These slopes are not the same, so you've got to get it through your head that the derivatives are finding the slope of the tangent line every single time.